what I think is a really good analogy for how acid-base titrations work in Monday night's class. So this is review. We covered this on Monday. For an acid-base titration, we're trying to figure out the concentration of an unknown solution using a known amount and known concentration solution. So you'll have a burette like this that has sodium hydroxide, and you'll know exactly what the concentration of that is. And then you'll be adding it to a flask that has acetic acid in it. And in that flask of acetic acid, there are these hydrogen ions, right, protons floating around in the solution. And your goal is to add as many hydroxides as there are hydrogens. And what this really is doing is letting us count the number of moles. And so that's why I showed you this one up here as well, where if there's some number of moles of H plus ions in the solution, adding more water or diluting it, as long as it's not an acid that we're adding or a base, doesn't change the number of moles of hydrogen. There's a set number of moles in that flask, determined by the initial amount that you added. So the analogy is this then. It's like if you were at a park and between 405 kids running around screaming all over the place, and you want to count how many kids are at this giant party. But because they're running around, you can't just count them because they keep shifting and moving. So instead, you can take a massive crate of ice cream sandwiches and hand out ice cream sandwiches. And if you have some way of making sure that each kid has just one ice cream sandwich, you can pass one to each kid, and then once every kid's gotten an ice cream sandwich, just count the number of ice cream sandwiches that you handed out. And that's the number of kids at the party. So when we're doing this acid-base titration, the sodium hydroxide up here, these are our ice cream sandwiches. We know how many of those we have, and based on how many come out of the burette and go to the kids in the flask, we know how many hydrogen ions were in the flask. And so we can use that number to calculate the concentration of the unknown solution. And then you'll know that you've gotten to the right number of kids and ice cream sandwiches when the flask turns pink. So that's what we're going to do in lab today. Okay, so moving on to the new stuff. We're just going to kind of touch on this and talk about the fact that these exist. So far, all of the acids that we've talked about and bases that we've talked about have been strong acids or strong bases. So when you add them to a solution, one of the hallmarks of a strong acid or strong base is that they ionize completely. But that doesn't happen with every single acid. So hydrofluoric acid, for example, is one that does not completely ionize in solution. And part of what that has to do with is the hydrogen and the fluorine really like each other, and so they have a stronger bond than the hydrogen and the chlorine. So the fluorines tend to hold on to more of their hydrogens, whereas the chlorines lose them all. And you actually saw this when we did the solutions and solubility lab, which if you can remember anything from before Thanksgiving break, was that last lab that we did. And you went around the room with the jars of different solutions and stuck those on the electrodes of light bulbs. The ones that lit up were strong electrolytes. One of those was hydrochloric acid. So strong acid ionizes completely and is able to conduct electricity also. So another piece of this, though, is that when you add something like hydrochloric acid into a solution, so this is the reaction here, that HCl, like I said, ionizes completely. So the hydrogens all become H3O+, and all the chlorines become Cl-. So if you have a 1 molar hydrochloric acid solution, this is another way to write the concentration of whatever's in the brackets, then you'll have exactly 1 molar H+ ions in the solution. And you'll also have exactly 1 molar Cl- in the solution, because every one of those HCl's carries one of each of those things with it. And then with those ions in solution, they'll conduct electricity. I think the only weak acid that we had, was glacial acetic acid. Remember if that one actually lit up dimly for anybody.
So pure water does not conduct electricity?
Pure water does not conduct electricity.
So what do they put to, how we use water in the dams and all that to create the electricity? What do they?
Oh.
How does that flow?
Yeah, so that's basically all of the ways that we conduct electricity or create electricity, generate electricity, involves spinning a motor. So if you take an electric motor and you spin it instead of using the motor to spin something, it generates electricity. And
also they use the water to use for the force to
Yep.
spin it.
Yep.
You know in the movies where they're like on the little bicycle,
Yeah.
like powers and like that.
Yeah. So here's a list of some strong acids. All of the acids that are formed with halides, so fluorine, chlorine, bromine, iodide, are all strong acids. That's one of the quick ways on the periodic table to recognize those. Nitric acid, perchloric acid, and sulfuric acid are also strong acids. Most strong acids are monoatomic, but sulfuric acid is one of the few that's, or monoprotic. Sulfuric acid is diprotic. So we did a problem with this last time too, where we neutralized some amount of, I think that was phosphoric acid, so it was triprotic. So this has two hydrogens that can each be ionized. So you would get, after losing one of them, you'd have H, SO4 minus, and then you could lose the second one to get SO4 2 minus. So weak acids do not ionize completely. They only ionize partially. And this is kind of getting to the next chapter a little bit. So this double arrow, and now I'm trying to remember if I mentioned it in this class, but we don't really talk about in Chem 20 very much about reversible reactions. They are all kind of going in one direction for Chem 20. This double arrow indicates partial ionization. It also indicates that the reaction is happening simultaneously in both directions. And we'll get more to exactly what that means in the next chapter and talk about equilibrium. So we're only getting partial ionization of hydrofluoric acid. So when you have a solution of, let's say, 1 molar hydrofluoric, you're not going to get all of the hydrogens off of all of the fluorines. So your concentration of H plus in the solution, so concentration of, or H3O plus, is going to be less than 1 molar. So you're going to have some concentration of H plus or H3O plus in the solution, but it's going to be less than whatever the concentration of the weak acid is. And then when it comes to conducting electricity, because there are fewer ions in the solution, it's also going to conduct electricity weakly. So I think there was like one solution that was reliably dim for the solutions in solubility lab, and that was the one weak, I think it was weak acid. I think it was glacial acetic acid. So weak acids are going to be, oh, I'm sorry, I misspoke earlier. Hydrofluoric acid is the one halide that's not a strong acid. So chlorine, bromine, and iodine are all strong. Hydrofluoric acid is the one weak halide acid. Then the other ones are what's called a carboxylic acid, or a lot of the other ones are carboxylic acids. So that's an organic chemistry functional group. It looks like this. So you've got a carbon, double bond to a hydrogen, single bond to an oxygen, and then the hydrogen that's on that oxygen is the one that's the weak acid. There are some other ones that we've looked at actually before. So sulfurous acid, carbonic acid, and phosphoric acid are also weak acids. And then these ones are diprotic, and then the phosphoric acid, which we saw before, is triprotic. Okay, so if we know that strong acids ionize completely, weak acids only ionize partially, which one of these is the weak acid? As long as the projectors. Yeah. So if it only ionizes partially, then there will be some of the original acid left in the solution.
Okay.
So A has, so this one would be hydroiodic acid, HI. Is there any HI left in the solution? Still bound together? No, right. It's all separated. They're all individual iodines or individual H3O+. So we go to the next one. This one's actually nitric acid. So is there any nitric acid left whole, unionized? Nothing in that one either. So process of elimination, but also, if we look at this one, and I guess admittedly this one's probably the hardest to see because the projectors are bad with red. We do have some, so like this is an H, so this is formic acid. HC, I don't know why I rewrote that because it already says it there. But there are more than just one of these in the, I thought I could flip that. There are more than one of these in the solution. So there's one up here, there's one over here. So all of these ones that have two hydrogens still attached, those are all still the formic acid that hasn't been ionized. There's actually only two H3O+ that have been ionized. So most of it's actually staying as the formic acid.
So C is the weakest?
So C here is the only weak acid. This is a strong acid. This is a strong acid. Yeah.
So, would like the good rule of thumb be like monoprotic or strong acids will always be monoprotic?
No. No, it's something that you do kind of have to memorize. Yeah. I don't have a mnemonic or anything. I know sulfuric, I mean like this list up here. I will say this, it's easier to memorize, oh, I think I missed it. It's easier to memorize the smaller list. So if you memorize the list that has all of the strong acids, I don't remember off the top of my head. I'm not confident enough to say which one is the smaller list off the top of my head. These lists both have 6 on them, but there are others outside of these lists. So either memorize the strong acids, which is my guess that there are more weak acids than strong acids. And then everything else will be a weak acid. So you can help yourself out that way. Okay. So some of you have probably already started on that pH worksheet. Oh wait, no, that's next. So here, determine the concentration of H3O+ in each solution. This is again coming back to whether it's a strong acid or a weak acid. I will say one rule of thumb is carboxylic acids are going to be weak acids. So this is going to be a carboxylic acid. Again, formic acid like we had before. So if this is a weak acid, I'll tell you that much. What's the concentration of H3O+ going to be in the solution? Less than
0.0? Oh, no.
why 1?
Oh, do that another time.
The other one was less than 1 because it was starting with 1 molar of the, yes, less than 0.50. Because it's a weak acid, it only partially ionizes, so you're only going to get some of whatever the initial acid concentration is. So then that's because this is a weak acid. So for B, 1.25 molar hydroiodic acid, is it a weak acid or a strong acid?
Strong.
It's a strong acid. So the concentration of H3O plus will be less than or equal to 1.25. Equal to. And that's again because it completely ionizes. So for every HI, when it reacts with water, you'll get H3O plus I minus. So for every one HI, you get one H3O plus.
So what would you get on the first one?
So on the first one, the equation's going to look the same, but we'll write it with the double arrow. Not H3, H2. So the double arrow meaning that this is happening in both directions. It also means that we're only partially ionizing. So, whoops. CHO2 minus. But because some of these H3O plus can react with the CHO2 minus or formate to go back in this direction, then you don't end up with the total amount in the solution. So for C, 0.75 molar hydrofluoric acid, is it a strong acid or a weak acid? It's a weak acid. And if it's a weak acid, that means the H3O plus concentration is less than 0.75 molar. So for any weak acid, the concentration is going to be less than what the concentration of the initial acid is.
So we just remember the element kind of, like you said, fluoride is weak, so we'll know that there's a fluoride
Hydrofluoric acid will always be a weak acid.
there.
Yeah. All right, so then analogously, there's also strong bases and weak bases. The biggest difference between a strong base and a strong acid is that for the polyprotic acids, so something like H2SO4, there's these ionizations happen one step at a time. So plus H2O, that'll give you HSO4 minus plus H3O plus. Let me write it this way, actually. And then that HSO4 minus will ionize again with another water to give SO42 minus plus another H3O plus. So they happen one step at a time. Every proton gets pulled off, or all of the first protons get pulled off, and then all the second protons get pulled off. For the bases, they don't ionize in multiple steps, they ionize all at once. So for these strong bases with two hydroxides in them, so strontium hydroxide, calcium hydroxide, and barium hydroxide, you get those two hydroxides out in one step. So then if you had a concentration of 1 molar strontium hydroxide, what would the concentration of hydroxide in the solution be? If we get 2 hydroxides for every 1 strontium hydroxide.
Two.
Yeah. Be 2 molar. So if there are 2 hydroxides, we get twice as much hydroxide. So just like the strong acids, though, strong bases do completely ionize. Yeah, they completely ionize. And these are, strong bases are easier to identify because they're always going to be a metal plus hydroxide. So a lot of them are going to be the alkali metals, so group 1, or alkali earth metals, group 2. Right, that's where these ones all come from. Lithium, sodium, and potassium are group 1. Strontium, calcium, and barium are all group 2. The weak bases are, in this class, almost always going to have nitrogen. So weak bases are analogous to weak acids in that they don't ionize completely, or that they don't create as many ions as their strong counterparts. So these were the ones that we talked about when we were going over the definitions of acids and bases. So ammonia is a weak base, is a Bronsted-Lowry weak base and not an Arrhenius weak base. So it reacts with water in the aqueous solution, pulls a hydrogen from there, and then creates hydroxide sort of indirectly. So in this equation, we have just generic B for weak base. So something reacting with water to form a positively charged ion and a hydroxide.
What's an example again of a weak base, like?
Ammonia, they're all going to be, so it's got like a nitrogen in it. There's actually,
Ammonia again?
huh?
What's ammonia again?
This NH3.
I know, but like, what is it? Like acids or like, you know?
Oh, it's a weak base.
I know, but like acids are things that you can use for cleaning supply.
Oh, ammonia is also used as a cleaning supply.
Oh, okay.
Yeah. This is when they say never mix ammonia and bleach. If you mix ammonia and bleach, then you create, I believe it's, well, chlorine gas or mustard gas. Not mustard gas, chlorine gas. It's, yeah, don't mix those. So NH3 is a weak base, and it's, again, creating fewer ions in the solution than a strong base would. Actually, let me go back to this. And we can do the same thing. If I say I have 1 molar ammonia, how many hydroxides, what concentration of hydroxide is going to be in the solution?
1.
You're going to be able to say less than 1. Yeah, I was going to say, you're not going to be able to say exactly, but it's going to be less than 1 molar. Can't have a negative, no. So like I said, a lot of these are going to have, almost all of them have some sort of nitrogen in them. So organic, they're called organic amines. So pyridine is one that we saw earlier, C5H5N. And it's that nitrogen that can steal a hydrogen or accept a proton, I guess I should use those terms, accept a proton from water to create OH minus. Or ethylamine, again, it's got some number of carbons, hydrogens, other things going on, but because it's got this nitrogen, it can react with water and form a hydroxide, which isn't to say not every compound that has nitrogen in it is going to act as a weak base, but in this class, that's one of the things that you can use to identify if it is a weak base. Okay, so similarly, we can do sort of the relative concentrations of each of these solutions. So if we have 0.055 molar barium hydroxide, the first thing you have to do is identify, is this a strong base or weak base?
Strong.
Strong base. So if this is a strong base, then the concentration of OH minus is going to be what? And this one does have a little extra twist to it.
Maybe 0.055.
Almost. How many hydroxides are there in barium hydroxide? 2. So if the concentration of this whole thing is 0.055, so we multiply it by 2, and so we'll get 2 hydroxides for every 1 barium hydroxide. So it'll be 0.110 molar. And then for B, is C5H5N a strong base or a weak base? What did I say about nitrogens? Yeah, weak base. So then the concentration of OH minus hydroxide will be, eraser, there you go. Yeah, less than 1.05 molar. And then for the last one, is sodium hydroxide a strong base or a weak base?
Strong.
Yeah. It's going to be a strong base, and then that makes the concentration of hydroxide
Would it just equal that?
mm-hmm,
So 0.45?
0.45, because sodium hydroxide only has one hydroxide. Okay. So strong bases are typically going to be a metal plus hydroxide. And then the weak bases generally going to contain nitrogen along with possibly carbon, usually hydrogen. Almost always hydrogen.
Well, no matter what, we see nitrogen, we know it's weak.
Mm-hmm. So those ones are a little bit more general than the acids. Okay. So water is amphoteric. And we mentioned this early on Monday. Amphoteric means that it can act as both an acid or a base. So you take a water molecule and react it with another water molecule, and one of them can be an acid and the other one can be a base, or vice versa. And this actually happens in pure water spontaneously all the time. So one acid will bump into, or sorry, not one acid, one water will bump into another water, and a proton will get exchanged. And then on the other side of that, you'll get an H3O plus, hydronium, and a hydroxide. So in pure water, the concentration of hydronium, H3O plus, and hydroxide are always going to be the same. Because for every one of those hydroxides that you create, you had to also create the hydronium, right? Because it's all being created from the water itself. So it happens to a very, very small extent. So it's kind of like water's acting as a weak acid and a weak base. And that quantity is known. It's 1.0 times 10 to the negative 7 molar. So that's the concentration. Very, very small concentration of acid and base present. So we can define this then as the ion product constant for water. And say if we take H3O plus times OH minus, that's going to equal 1 times 10 to the negative 14. And this is how, if you haven't done the pH worksheet yet, this is how you convert from, or the easiest way to convert from H3O plus to OH minus, is you use this as an equation. So for any neutral solution, those two concentrations will be the same. So whenever we're adding acid or base to something, we're shifting this distribution. We're destroying more of the H3O plus to create more OH minus, or we're destroying the OH minus to create more H3O plus, and kind of shifts back and forth between those two. But they will always add up to, or multiply to get 1 times 10 to the negative 14. So if we know that in a neutral solution, it's 1 times 10 to the, or the concentration of each of these is 1 times 10 to the negative 7. Then in an acidic solution, the concentration of H3O plus is higher. And because this has to be true, because this has to be true, then that means that the hydroxide concentration has to go down. In a basic solution, we have a concentration of hydroxide that's greater than 1 times 10 to the negative 7, which means that the H3O plus concentration has to go down. It's kind of like like old school scales, or the scales of, wait, who's it that's holding that? The scales of justice. Right, where there's the two scales, so if you put something on one, it goes down, and the other one goes up. On The Price is Right? Yeah. There's a famous statue.
No, I know what you're.
Yeah. Okay. So there's this balancing act between the two. And that makes them interdependent. So if we're looking at just the concentrations of H3O plus and OH minus, I have to check and make sure how good this looks. So this is 10 to the negative 0. Down here is 10 to the minus 14. Up here, this is 10 to the minus 14. And 10 to the minus 0. So it just sort of illustrates that as we get more acidic, and this is something that I know can be confusing about exponents. So if you have a negative exponent, a smaller negative exponent, like this is 10 to the minus 3, just in case you can't see it, that's a larger number. So this would be 0.001. 10 to the minus 7 would be 0.0000001. All right, so smaller negative exponent means a larger number. So we're getting larger concentrations, that makes it more acidic, but then that also means that we have smaller concentrations of the OH minus. All right, so we want to calculate, we can use this to calculate stuff. And I don't think that these calculations are super difficult. There's a simple formula for it, which is why I gave you the pH worksheet though, so that you can just run through them. Because if you're getting numbers that are significantly different from that key, then you're doing something wrong probably in your calculator in the way that you're typing those in. And you should either talk to a tutor about it or come to me. I would be happy to help you figure out what you're doing on your calculator. That being said, too, you should get out your calculator right now. And make sure that you're getting the same things that I'm getting. So the conversion that we're going to be using here, right, is this H3O plus times OH minus is equal to 1 times 10 to the negative 14. So if we want to calculate the concentration of hydroxide, we can plug in this concentration for OH minus and then solve for H3O plus. Yeah, here, I'll do it over here. And show you the algebra. So the H3O plus concentration is what we want to know. This is going to be times 1.5 times 10 to the negative 2. 1 times 10 to the negative 14. Divide both sides by 1.5 times 10 to the negative 2. So then H3O plus is 1 times 10 to the minus 14 over 1.5 times 10 to the negative 2. Okay, so 1 e to the negative 14 divided by 1.5 e to the negative 2. So this first one is 6 point, with the correct sig fig, 6.7 times 10 to the negative 13. And if you're still not using that E button, which means exponent, should be doing that. So that would look like 1E negative 14 on the calculator divided by 1.5 E to the negative 2. If you don't, this problem is not going to, actually, let me think about this for a second. This kind of problem might give you trouble if you don't use parentheses and you don't use the E. If you use that E, it means times 10 raised to whatever the next number is, and the calculator knows to hold that whole number together. So it knows to keep this all together. You don't need to add parentheses.
I had to use the log button, the negative and then the log button.
We'll talk about the log button. Yeah. Okay, so this is the algebra for this. I'm not going to do it for the rest of them. For this next one, though, OH minus concentration is 1 times 10 to the negative 7. So what's the H3O plus concentration? Don't even...
I did the calculation on the top and it gave me something different.
Let me double check.
0.33 times 10 to negative 13.
You have 3?
I did 1 times 10.
Did you do 1.5?
1.10. Oh no, not 1.10.
So it should be 1 on top and then 1.5. I think you missed the 1.5 because you got the right exponent, but you got the wrong decimal portion. Anybody else get a different answer on their calculator for this one? Are you sure?
I got 6.6666.
Yeah.
Times
So rounded it.
to negative 13.
Yeah. So rounded it to two significant figures.
So where's the answer?
Yeah. If you have other calculator problems, we can talk after. Okay. This next one, though, you can do this one without even doing a calculation. So what is the concentration of H3O plus just based on this?
You just put the 1 times 10 to negative 14 underneath on the second one?
I mean, it'll end up being the same thing as this. So you'll get 1 times 10 to the 14, negative 14 over 1 times 10 to the negative 7. But what is this solution, would this solution be acidic, basic, or neutral? Yeah, this would be a neutral solution. So in a neutral solution, OH minus is 1 times 10 to the negative 7, and H3O plus is 1 times 10 to the negative 7. I should put units on this. So this is just going to be 1.0 times 10 to the negative 7 molar, 0 plus any brackets there. So this one's neutral, and I forgot that this is also part of this.
Is it neutral because we're basically using the scale you showed us?
Yeah. So typically typically most applications outside of the classroom talk about things in terms of the H3O plus concentration. And so that's the one that maybe will be the most familiar. For this first one, we should have done this also, is this solution. So it's got 1 times 10 to the negative 2 molar OH minus and 6.7 times 10 to the negative 3 molar H3O plus. Is that solution acidic, basic, or neutral? I can go up to this chart, actually. Yeah, it's basic. So that's like 1 times 10 to the negative 13. So this would be basic. And it's basic because the concentration of our acid is really small. Right? 1 times 10 to the negative 13 is a really small number. And then for the last one, This one you should calculate. That's not going to be easy to do in your head. But it again is the same H3O plus OH minus equals 1 times 10 to the negative 14. And so if we rearrange this, then H3O plus is going to be equal to 1 times 10 to the minus 14 over 8.2 times 10 to the negative 10, because that's the molarity of OH minus.
Does it matter which one's on top, which one's on the bottom?
It does matter. Yes.
Or why is that one on the bottom? On the first one, we put it at the top. On this one, on the top. Okay.
Yeah, it also ended up on the bottom. So then this is 1.2 times 10 to the negative 5. So another way you can, with just the concentrations, another way that you can figure out if it's acidic or basic is this concentration larger than 1 times 10 to the negative 7? So is the concentration of the acid larger than 1 times 10 to the negative 7? Is this solution acidic, basic, or neutral? Mm-hmm. So this one's going to be acidic. Go back and circle all these. So it's one acid-base calculation that we're going to do. This is a little bit cumbersome, though, when you're talking about acids and bases, to say that it's 1 times 10 to the negative 7 molar of this concentration, molar of H3O plus or OH minus. So we have another scale called the pH scale. You've probably heard of like alkaline water, just like pH 8.5 water. So that's water that's slightly basic. I don't think it really does anything, but it's a thing that you can buy now. So this reduces those concentrations down to much, much, much smaller, easier to say numbers. And the pH scale goes from 1 being strongly acidic, and we'll see why that's 1, and then 14 is strongly basic. Also, if you've ever had to manage a pool, you need to be checking the pH all the time. That's what this is. This is the exact same scale that's being used there. So if the pH is less than 7, you're acidic. pH greater than 7, it's basic. pH equal to 7, neutral. And then the reason that these numbers get smaller is because this is a logarithmic scale. So a logarithmic scale works a little differently from other numbers. So for every pH, this 4 is representing times 10 to the negative 4. So if this one dot represents times 10 to the negative 4, then a pH of 3 is actually a 10 times higher concentration than that. So it goes from 10 to the minus 4, and do this to 0.0001 molar, and this would be 0.001 molar. So 10 times larger, and then going to pH 2, it's 10 times larger than 10 times larger, so it's 100 times more than pH 4. So this would be 1.01 molar. So usually when we're talking about pH and stuff, it's really going from pH 3 to pH 4 is a huge change in the concentration. 10x. Okay, so now I'm going to try and explain logarithms. Logarithms are just, I think, inherently unintuitive. So what a logarithm is actually doing, if we want to take the log, let's say we want to take the log of 10. There are two different types of logarithms. I always write natural logarithms as ln, And the natural logarithm has what's called a base, and that base is e, which is like 3.16 something, 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 something. It's a number that it calculated. It's a special number. I'm not a mathematician. I don't remember why it's special. The log log, which is the one that we're using here, is log base 10. And if you have one of these calculators, there's one button that does both of those. So if you press it once, it gives you the natural log. If you press it twice, it gives you the log base 10. And that log base 10 is what you want to use. All right, so what does that even mean, though? When you write this function, log base 10 of 10, it's asking you, if I raise 10 to what number, so what exponent of 10 will give me the number that's in these parentheses. And when there are whole multiples of 10, it's pretty easy because it's just the number of decimal places. So for 10, the decimal's here. We'd have to move it over 1. So 10 raised to the first power would be the result of this logarithm. You don't really need to know specifically how to calculate these without a calculator. In fact, if you even know what a slide rule is, that's how they used to do this before they had calculators that could do logs. So if we did the log base 10 of 100, what would that answer be? So 10 to the 2. And so that's moving over moving over 2 decimal places. And you could do this for the logarithms where it's just 1 and then a bunch of zeros. You could do those without having to type it into a calculator. And then if I did log, we'll do one more, like this. So what would log base 10 of 1,000 be? Yeah, times 10 to the 3. So for numbers that are larger than 1, we get positive exponents. If I switch this up now and I say, what is the log base 10 of 0.1? Any number that's less than 1 is going to give us a negative result for a log base 10. So the log base 10 of 0.1 is going to be negative 1. Oh, I'm sorry. Well, okay. This is... The answer to this is just 1. It's just 2. It's just 3. Because it's answering the question of what goes into this spot. So
No 10.
So this is going to be 1. This is going to be 2. This is going to be 3. So the log base 10 of 0.1 is negative 1, because the question you're answering is, if I raise 10 to what number will give me that? So negative 1. So So log base 10 of 0.01 would be what number? Yeah, just negative 2. And then just one more because it's helpful to see patterns, right? So 0.001 would be negative 3. So every time you go down 10 times smaller, then you get another exponent here. So when we're doing these logarithms, the negative log of the H3O plus concentration to get pH, so now it's the negative log of, let's say, 0.001. So that's like this one that we did here, but now we're just multiplying whatever this is by a negative 1. So it gives us a positive number. It's positive 3. All of that to say that this is how you calculate pH. All right, so pH is the negative log of H3O plus. And it's because it can be a little bit tricky to use logarithms on a calculator that I want you to do the pH worksheet and just do it a bunch of times. So you get that muscle memory for how to type it into your calculator. Okay. So we can calculate. What is the question? Oh, actually. Yeah. Sorry. There's one more thing I wanted to do with this. Okay. So you get nice whole numbers if you have just 1 and zeros. If it's anything else, that's where the decimals come from. So let's say we have the negative log of, say, 9.2 times 10 to the negative 4. This one you can't do. Well, if you can do this in your head, I'll be thoroughly impressed. So if I take the negative log of 9.2 e to the negative 4, that's going to give me 3.0362. So the 3 is only telling me how many decimal places I move over. The rest of this is actually what the significant figures are. So for logarithms, this first ones place is never significant. You start counting significant digits after that. So if I do negative log of, let's do 4.111 times 10 to the negative 4. So how many significant figures is that? It's not the logarithm yet. So this is 4. The result of this should have 4 places after the ones place.
So now everything that we've learned about significant figures feels like a lie.
Nope, it's only different for logarithms. So this number that comes out of this is going to be 3.386052. I'm writing too many. So if we want 4 sig figs for this, it's going to be 3.386, rounds up, so 1. So these are the 4 significant figures. I know logarithms change everything. This is why logarithms are weird.
What about that one, the 3.0362?
Oh, this one would have been, since this is just 2 sig figs, this would be 3.04. So we'd start counting here. Oops. 1, 2. Okay. And most of the time, it's not going to be nice whole numbers. So, and calculate the pH of each solution, indicate whether the solution is acidic or basic. All right, so we just saw it. How do we calculate pH?
1 times 10 to negative 14 above.
That's how we would go to OH minus. But here we just want to calculate pH. Yeah, so it'll be the negative log of whatever this H3O plus concentration is. So 9.5 times 10 to the negative 9. So you do, oh yeah, this is, I wish this, it's like trying to use, oh no, it's still kind of working. Can you track my face though, please? Thank you. Oh, but that's not plugged in. This is the reason I don't use the on-screen is because I have like this calculator.
Yeah.
But the reason I don't use this is because it does not look the same as what your calculator is going to look like at all. So the way that you'll do this is there's a negative button, bottom right. And so you'll do the negative, and then this depends on which calculator you have. You need to figure out where your log button is.
It says log on here?
It'll say log somewhere. On that calculator, you might have to hit second and then, okay, one of those up here. And then find the log. So it might be like blue text above a button. So you do the second, and then on this calculator, you have to press that log button twice to get LOG, and then it's 9.5 e to the negative 9.
But just took log and then put that,
Make sure you put the negative sign first.
oh, I have to put the negative?
Yeah,
Mhm.
make sure it's the negative sign and not the
Do we
fraction
always
sign.
have to close the parentheses?
You should close the parentheses. You don't always have to. Sometimes it will complain.
YouTube video.
If you get, what is that error? If you get domain error, that means that you put the negative inside the log. You can't take the log of a negative number. So how many sig figs should this have? 2. So it's going to be 8.02. So is it acidic, basic, or neutral? So if it's less than 7, if pH is less than 7, then it's acidic.
Basic.
So this is basic. So it's larger than 7.
Oh, I was looking at the exponent. The 10 minus 9.
Yeah, so this 10 to the minus 9, then you have to use the other scale that's for the H3O plus concentration. Oh yeah, so it's basic.
Log is always negative? You always put negative?
When you're calculating pH.
Yeah.
Yeah.
So
'Cause-
this is how you want us to solve the worksheet?
Yep. And so basically every part of this, and we're going to talk about, we're going to get to some more of these conversions also. So then calculating this next one, it's just going to be the negative log of 6.1 times 10 to the negative 3. So it'll be 2.21467, but what would the final answer be? 2.21.
pH.
Because that first number is never significant. These ones are significant. I'm struggling. So is that acidic, basic, or neutral? Yeah. Be acidic because it's less than 7. All right, so the reverse of a logarithm. So remember the log of, put the log base 10 here, of whatever number is asking the question. So 10 raised to what number equals x. So the question mark would be here. So if we want to do the opposite of a logarithm, we do 10 raised to, for pH specifically, 10 raised to the negative pH. And that's the reverse of the negative log base 10 of H3O plus. So to reverse a log, you just raise it to, you make it the exponent of 10. And then because we use negative log to get pH, we have to use the negative exponent to get back to H3O plus concentration. And again, this is why I have you do so many on your calculator on that worksheet, and why it's just about doing them. Okay. So if we have a H3O plus concentration for a solution with a pH of, so for pH equals 8.37, then to calculate H3O plus concentration, that's going to be 10 raised to the negative 8.37. And then how many sig figs does a pH of 8.37 have? 2. So take your calculator, 10 raised to the negative 8.37. Oops. And that's going to be 4.2658 times 10 to the negative 9. And then the correct number of sig figs will be 4.3. So some calculators, like the TA36X Pro that I have, there's like a 10. Well, there's a couple ways you could do this. You can type in 10, and then there's a, you press the X raised to the box. Actually, it's a solid box. Or there's just a number that, or a button that's 10 raised to a box, and then it lets you type into that box.
For this one, you count the normal sig fig?
Yeah, so when you're going, the only thing you need to know is that the pH that you're starting with, only the stuff after the decimal place count as sig figs. So then, because this has only 2 decimal places in the pH, then we only keep 2 we keep 2 sig figs for the answer that comes out. And then it's like normal after that. Almost there. Okay, so that's H3O plus and pH. POH uses the same mathematical operations to calculate. So POH is just the negative log of the OH minus concentration. The only thing that's different is that you're starting with the concentration of hydroxide instead of hydronium. And then if you want to convert between pH and POH, I'm going to show you this derivation real quick. And it starts with the fact that H3O plus times OH minus equals 10 to the negative 14. And then we can take the log of both sides. So we take the negative, or we take the log of this side, and then the log of this. Now this is the log of H3O plus times OH minus equals, and we can do the log of 10 raised to the negative 14. So this will just be negative 14. And then I'm going to take that negative and I'm going to distribute it over to the other side, or multiply both sides by a negative 1 to move that negative over. So now it's the negative log of H3O plus times OH minus equals 14. And there's another fun property of logs, that if 2 things inside the log are being multiplied together, that's the same as the log of one of them. Well, it's the log of one plus the log of the other, but that negative gets distributed. So it's going to be minus the log of OH minus equals 14. And what is the negative log of H3O plus equal to? How do we calculate? Yeah, pH. So we can take that. It's a good question. I actually don't know if it stands for anything. Aside from that, it's the logarithmic scale of acid concentration. So negative log of H3O plus is pH, and the negative log of OH minus is OH, or POH, sorry. And that equals 14. So you can convert from pH to POH by plugging one of them in here and then solving for it, because the two together will always add up to 14. And then do you need to add another slide for this, actually? Yeah. So there's this. Let me do it this. So if I make this, I'm gonna make a box. So for converting between all of these things, we now have a bunch of different ways to convert, and it actually creates a sort of circle or box of conversions. So if you want to go from H3O plus to OH minus or back, then you use H3O plus times OH minus equals 10 to the minus 14. And then we can convert between pH and POH, because pH plus POH equals 14. And then to go from pH to H3O plus, that's 10 raised to the negative pH. To go from H3O plus to pH, that's the negative log of H3O plus. And then it's a very similar thing on this side, where it's negative log of OH minus to get POH. And then 10 raised to the negative POH will give you OH minus. So you can really convert around in circles. And this will be very helpful on that pH worksheet. Because this, I'm having you do on that worksheet each side of this thing, as well as having you go from corner to corner, actually. And so there's always multiple ways that you can go from, if you wanted to go from H3O plus to POH, then you could go this way to pH and then to POH, or you could go this way to OH minus and then to POH. I didn't quite finish. Well, you can do this last one here, and then the buffers is, I'll just speed through buffers real quick. So to calculate POH, 10 raised to the negative 4.25, because POH equals 10 raised, OH minus 10 raised to the negative 4.25. This is going to be 5.6234 times 10 to the negative 5. And the same rules for pH in terms of sig figs, same rules for pH apply to POH, because it's still a logarithm. So this will only have two sig figs. So it'll be 5.6 times 10 to the negative 5 molar OH minus. And very quickly, this, aside from addressing that it's a thing, doesn't really come into play in this class. You'll talk about this way more in Chem 2, if you take Chem 2. So buffers have significant amounts of both a weak acid and its conjugate base. So remember, conjugate base is just sort of after an acid donates a proton, it becomes the conjugate base because it can accept a proton. So human blood is a buffer, and it's actually carbonic acid that acts as that buffer. So healthy people are about 7.36 to 7.4. If your pH gets below or above that, then you die. There's diabetic ketoacidosis, is when your blood pH starts to get too low because your body's processing too many fats into ketones. I think it's fats into ketones. And your blood is basically being overloaded with acidic ketones. So it throws that out of balance. So you can have an acetic acid or sodium acetate buffer system. So adding base to acetic acid creates sodium acetate. And then when acid is added, then acid will react with the sodium acetate to create acetic acid. And so if you have a lot of acetic acid and a lot of sodium acetate together, any extra acid or base that you add will just use up some of acetic acid or some of the sodium acetate. And so because of that, it holds the pH fairly constant until you run out, and then the pH goes wild, which is what happens in diabetic ketoacidosis, or ketoacidosis in general. Yeah, so it's just balancing those two things.